Okay, so here we have the 2003 Form B question 2. We have two equations, and it looks like initially when we look at circles, we think polar. But the equations presented are written in rectangular coordinate points. They provide the intersection point, one of which is 1, 1. The other one is 1, -1 below there. Because we're looking at finding the area of the region R, if you look at part A, it's asking us to find it with respect to x. That represents that region R. So with respect to x means dx. We're in rectangular coordinate points, has nothing to do with polar at the moment. So what we're really finding in part A is the area with respect to x. If we look at where the intersection falls, that actually divides the region into two parts. You have here, this region is defined by the top of the circle, the smaller circle, minus 0, versus this region on the right is the top is going to be the larger circle minus the x-axis. So it's back to top minus bottom, representative rectangle, the area of each rectangle divided so that each width is dx. And this is first semester stuff. So first, if we need the area with respect to x, we need the equation solved for y so that it's isolated. So y squared equals 2 minus x squared. Y equals the square root of 2 minus x squared. And then go ahead and do the same thing on the other equation. The x squared plus y squared equals 2 is the one centered at the origin, and that's the bigger circle. So I'm going to go ahead and just write here, this is the bigger circle, this is smaller circle. Okay, so now looking at the region, we'll start with the left region, which is the smaller circle minus 0. So the integral is going to go from 0 to 1, x value 0 to 1. Smaller circle is square root of 1 minus x minus 1 squared. That's the y value. Technically minus a 0. We don't need a square because this is, remember, this is represents your height, and then this is your width. It's a rectangle. And then secondly, we're going to do the area to the right of that, which is the bigger circle. And the bigger circle would be going from 1 to whatever x value this is. So to find that x value, if you guys look, that's the x-axis of the circle centered at 0. So if you plug in 0 for y, you get x squared equals 2, or x equals radical 2. So 1 to radical 2 of your smaller circle, which is the square root of, your bigger circle, which is the square root of 2 minus x squared. So again, that's your bigger circle here. Minus 0 here, so to represent this area. So square root of 2 minus x squared dx. Okay, that's one way of writing it. The other solution that they provided was in recognizing that what I'm highlighting in pink here, that actually represents a quarter of a circle. So using geometry, you know that circle, a quarter of the area of a circle formula would be 1/4 pi r squared, and the radius of that smaller circle happens to be, let's see, it's 1, right? So the length of this radius here is 1. So 1/4 pi, and then 1 squared. So then from there, you guys can see that you're adding the second part, and that is just a portion of a circle, but we can't tell what the portion is, so we can't apply geometry to it. So that one's going to have the same setup for the integral as we had it in the above equation. So that's how you would do part A. Part B now is asking you to do the same exact thing, but everything in terms of y. So if we take a look at the equation in terms of y, that means our rectangle is going to go in the opposite direction. It's going to go in this way. And if we look, the first rectangle is the right minus the left, and that's consistently true throughout the region, that the right is your bigger circle minus the left, which is your smaller circle. The only difference is that with respect to y means that we have to solve all our equations so that it's in terms of y. So I'm going to do that down below here. So x squared equals 2 minus y squared, and go ahead and solve both equations for that. So this is again the big circle. This is the little circle. Now for part B, areas with respect to y, and we're going to look at it going from the lowest y value to the highest y value, so 0 to 1. The integral from 0 to 1. And this time we only need a single integral. The right integral would be the larger circle, so the larger circle being the square root of 2 minus y squared. And then the left circle is minus the square root of 1 minus y squared plus 1. So sorry, that says y squared. That's with respect to y. Okay, then, and all these are just setups and not actually calculating it because it was a non-calculator question. Now they redefine the two equations and they say the polar equations of the circles are r equals the square root of 2 and r equals 2 cosine of theta. And they want us to set up an expression involving one or more integrals with respect to the polar angle that represents the area of r. So what we want to do is think of these now as sectors instead of rectangles. So if I think of it as sectors, I'm going to go ahead and zoom in here. We want the sector right here where up until that, the function that defines this area right here is going to be the polar curve of the larger circle. And then we're going to add the area of the sectors that span the smaller circle. And so what we do is we need to know what this angle measure is right here. So that's the intersection point between the two equations. So if we set square root of 2, the two equations equal to each other, 2 cosine of theta, solve for it. This is intersection. And we get rad 2 over 2. So theta equals pi over 4. So this is pi over 4. So let's start off with this region right here with the sectors right here. So that's defined by the equation r equals the square root of 2. Okay, so that's your larger circle. So this is large circle, this is small circle. Okay, so our area is going to be equal to, there's going to be two integrals here. So the first integral, we can go from 0 to pi over 4 of 1/2 r squared. And r in this case is radical 2 quantity squared d theta. And then we're going to add 1/2, and then we're going to go from pick up from pi over 4 and go on to pi over 2. Pi over 2 is where this circle will eventually wrap back around to the origin and integrate the equation of the radius squared. You can also think of finding the area of this region. If you want to, you guys can simplify that further. But in this case, it just asked us to set up an expression that involves integrals with respect to the polar angle theta.